Hello, everyone. My name is Gina Oliver, and I worked with Will Lewandowski this summer, and we looked at anisotropy from split direct S and SKS to look at lithospheric fondering under the Sierra Nevada in California. And one of our big questions is, can seismic anisotropy in one place tell us something about continental crust evolution? And so we know that the Earth is primarily made up of mafic oceanic crust, and yet we do have felsic continental crust. And so it brings up a lot of questions. Why isn't there a mixed crust, or why do we have two different types? And so we wanted to look in this area to see if maybe we can find out how this happened. So we wanted to start off with what seismic anisotropy is. And it's the idea that seismic wave speeds are directionally dependent. And in an anisotropic volume, it's material that has different orientations. And so when an incident shear wave comes in contact with an anisotropic volume, the energy splits orthogonally into two polarized planes. And so you get, in this blue, you get the S fast, and in the red, you get an S slow wave. And these split lag times are recorded at the seismic stations right here. And why we want to study the Sierra Nevada. So this batholith was formed from a Mesozoic magmatic arc, and it's thought to look like the modern Andes. It supports a high elevation in spite of thin crust, and it's also mostly made up of a felsic composition. And so we're going to focus, this study is focusing mostly on the southern Sierras in particular. So what's going on underneath the Sierra Nevada? So the batholith went under a differentiation process where it has the felsic composition on top with a more dense mafic material on the bottom. And with the Miocene xenolith studies, it shows about 10 million years ago, the ultramafic root was intact underneath. And with Pliocene xenolith studies, about 3 million, it showed that this root is not in exactly the same spot. And so it must have moved, something must be happening underneath. And many hypotheses support that maybe this root is falling or recycling back into the mantle. And if this is happening somehow, then this would cause convection and causing hot, buoyant asthenosphere to rise up and cause an isostatic response or a lifting of the Sierra Nevada, giving evidence to why it's so high. And the Sierra Nevada is a really interesting place because if this can tell us why we preserve felsic continental crust, this area is going through its intermediate phase, so we can do many studies to see how these processes occur. And if there is a sinking root or fondering lithosphere, then this would give great explanation to the Isabel Anomaly, which is a high seismic velocity area depicted in these cross-sections from the Basin and Range to the Great Valley. And this is a Isabel Anomaly just southwest of the Sierras. So this is characterized as a colder, dense area, so it might maybe be the root coming off and going back into the mantle. Okay, so what we wanted to do partly is we wanted to look at the depth of anisotropy. And there's already been SKS studies done. And what an SKS wave is an S wave that goes through the mantle, and then once it gets into the outer core, it becomes a P wave, and then once back into the mantle, it becomes an S wave. And so what we wanted to do is we wanted to use direct S waves to look at the same area. And what we wanted to do is we were looking for this hypothetical single layer of anisotropy, and we wanted to see the depth at which best describes both the SKS and the direct S wave data. Okay, so from this previous SKS data, the observations was that it corresponded to absolute plate motion, and so it did give us the S fast and S slow. And what we were really looking for in this study was discontinuity in anisotropy from absolute plate motion. And to illustrate this, here are some cartoons. We already know that there is anisotropy caused by absolute plate motion right here. And what we were looking for was something different, some disalignment in absolute plate motion, perhaps caused by lithospheric fondering from the southern Sierra. Or another hypothesis, that it's in the crust. And if it was, that it probably wouldn't help out this research, but it might be really interesting to other research as well. Okay, and so our data set comes from the Sierran paradox experiment. And this was 27 stations that recorded 15 events shown from this global seismicity plot. Then each one of these red dots are the earthquake events. And these waves are coming in at different trajectories into and recorded at the stations. And what I looked at most of this summer was these raw waveforms. And I picked these out of a program called SAC. And it shows the S fast coming in. And I was looking at the difference between the peak and trough times in which the S flow wave arrived in. And that's what we looked at. Okay. And so now we have the SKS and the direct S data. And so we took this method called Popper's tomography method. And it's the idea, it's mapping the residuals and then back projecting down the ray path to find exactly where this layer of anisotropy is. And we compared those back projections to a variety of depths. So to see what best agreed with both the SKS and S wave data. And some of our results are really cool. So these figures are looking at the back projected direct S minus the SKS to see where they both agree at what different depths. And so on these, we have 50 kilometers, 150, 200, and 250. And what we're looking at here is where the Isabel Anomaly is. This is just geographical reference. Our stations and our SKS splitting are those little ones. And we wanted to get as close to 0 as possible. And we looked at each of these depths. And the depth between 150 and 200 kilometers was the best fit of these data sets. Okay. And so we wanted to compare this to absolute plate motion, and we wanted to look at the two data sets. And so this SKS that with absolute is shown in this right here. And the more red you get, the more splitting is occurring. And what we're seeing, this is a graph of direct S at 200 kilometers. And so we're looking at the anisotropy at this depth. And we see that here it corresponds with absolute plate motion, and here as well. But there is a distinct area that there's some form of different flow going on. Something else is happening. There's isotropic or something else. And that it's kind of aligning with the Sierra Nevada or the Isabel Anomaly. So with these really interesting results, we did compare our results to a couple other characteristics of the area. So here's our results right here. And our interpretations that we concluded was from A to A prime in this area of direct flow that maybe there's some lithospheric fondering happening, and that's why it's causing a different flow to occur. And from B to B prime, this is where it's most distinctly absolute plate motion. And this coincides with other studies, with p-velocity studies. And in this same area of different flow, we see a cliff from low velocity areas characterizing like a hot material from a more cold high velocity area. And so maybe if this thing is coming off somehow, it's bringing up hot asthenosphere, and then you can see the fondering route perhaps. And this also corresponded with a compositional topography graph where here it's showing a more felsic composition in the area of different flow, and then also in between you have an intermediate composition. So maybe if it is fondering, then what you're left with is this felsic part up here. And so this area is extremely interesting to study because, you know, research needs to be done, but it's very interesting. If we can understand the processes in this area, then maybe it's going to give us some insight in how we preserve continental crust. So I do want to thank everyone, especially my mentor, Lewandowski, who's been really awesome, UNAVCO RESESS, the NSF, and everyone else who's helped out. Thank you very much.
Is it possible that the Sierra Nevadas never had ultramafic root and that the xenoliths were part of the old Farallon plate? Or I guess how would you even be able to tell?
There's been a lot of studies in the area that's shown that it's most that there was a dense, like a root there somehow. Especially, yeah, if it went through a differentiation process, like it had been there somehow. Cool.
Okay. Do you have any thoughts, or have you read anything in the literature about why this detached root is only in the southern Sierra, like only such a limited area, rather than extending further along the Sierra Nevada or up north or something?
Yeah. So there's a lot of hypotheses that mean like many different things, and this like kind of removing is one of them. And I don't know exactly why in just the Sierra. I guess maybe parts of it, and in other areas it is attached. And so I'm not entirely sure. I don't know if will we give you insight. Yeah.
Did you want to comment?
If you wanted to.
If you want my opinion, anyway.
Yeah.
It may well be the case that the Southern Sierra was originally a thicker, better differentiated batholith than the Northern Sierra, and it manifests not only in the elevation but also in the geomorphology and the composition going from the Southern Sierra to the Northern Sierra. And so it seems most likely that this foundering process requires a well-differentiated batholith to have this sort of whole-scale delamination style recycling of mafic material.
More dense stuff going back in.
I was just wondering what the paradox in the Sierran paradox experiment was.
I think that's just what it was named. I know that given the data set, so yeah, that whole idea. Supporting thin crust. Why is it so high? I don't know.
Great.
There's a lot of paradoxical things going on in the Sierras, I'm assuming.